it says, what's that? Yeah, the printer is not quite working. So you don't have to write all this down, but this is generally how I try to think of these problems, and I'll show you how to kind of work through this. A farmer is making a pen out of 480 yards of fence. He will be dividing the pen into 3 sections that are all equal in size. What dimensions should he make the pen to maximize the area? Now, this would be a basic problem. I expect that you guys could do this problem on the test on Thursday. Okay, this is one that you've seen last year. Now I'm just going to ask you to apply calculus. We don't have time to cover all the optimization problems we would like to, but we could cover a few. Okay, and then after you test, we'll cover some of the more difficult ones, which you won't be tested on, but we will work on in class. So these are pretty good problems. The first thing I like to do is I like to model the problem, and I like to generate a picture. So what I do here is I draw a rectangular fence area like such. He's going to divide the pen into 3 sections. So like that, all equal in size. What dimension should they be? Now, there's kind of a trick here, I suppose. First of all, what are we trying to maximize? Area. So I need a formula for area. Area is equal to, or length times width, okay? Now, I don't know what the length of the width is, but if I call this W, if I call that W, what would be, this top and bottom piece would be L, right? Well, before I label those, let me just write something else down. Okay, so I have L and L, and those are going to equal something important. If I add up the 4 W's and the 2 L's, what do I get? $480. My fencing. 4W plus 2L is equal to the 480 yards of fencing that I get to use. So if I can solve for L in terms of W, I will be able to write an equation or a function that models that. How do you solve for L? 2L equals 480 minus 2W divided by 2L is equal to 240 minus W. So I've expressed my formula and my relationship. What did I do? Whoops, sorry. So 480 minus 4W, we divide by 2, we get 240 minus 2W. There you go. So I know that my length is 240 minus 2W. Now, you guys, I know very well that the most difficult part of this problem is setting it up. So, you need to see a number of examples and be able to apply it. But I think whether we divide into 3 sections, 5 sections, 8 sections, you should be able to do this type of problem. Agreed? Now that you've seen it. So I've divided up in these appropriate sections. I can now write a function for my formula right here. Namely, that the area in terms of what is my variable that I'm working with? I've written it all now in terms of W. The area in terms of W is equal to L, which is 240 minus 2W times W, or my area in terms of W is going to be equal to 240W minus 2W squared. Now, let's see how easy that is to solve. Notice right away from the outset that we are asked to maximize the area. Well, that sounds like a kind of a challenging problem. What dimension should I make it so as to make that true? Well, knowing calculus, we know how to maximize things pretty well. What shape is this if I were to graph it? It's a parabola. Does it go up or down? Down because of the negative 2W squared. So it goes down. So I naturally have a maximum. Maximum occurs when the derivative is equal to, so let's just solve it. Let's find the derivative. A prime of W is equal to what? 240 minus 4W. I find local maxes and local mins when I set it equal to 0 and solve. 0 equals 240 minus 4W. W is equal to 6. How would I find my length? Plug that back in to find my length right here. If you plug it back into your original function, that will give you your area. We don't want area. We want the... Okay, so I plug it back in. Oh, 60, I'm sorry. If I plug 60 back in, I get 240 minus 120 is 120. So length is 120, width is 60. That is enough information. There we have our formula. So notice how quickly calculus allowed us to solve that. Now, that may not be as impressive of a problem because you guys say, well, we know something about quadratics. We could have found the vertex very easily using quadratics. Well, what if we don't know how to find the vertex? What if we have a problem that doesn't have a vertex? Let's look at the example right, yeah, number 5. A box with an open top is to be constructed to form a rectangular piece of cardboard with dimensions 10 by 18 by cutting a square from each corner and folding the sides up. Find the largest volume that a box can have. So I'm going to model the problem. And you guys, when I was your age, I used to try to kind of skip through certain steps because I was like, I probably don't need to do it the way that the instructor is necessarily telling me. And that's fine. Do it however you want. But at the end of the day, if I'm going to sit down and do something that I haven't seen before, this is now the approach I use 100% of the time. So I use these 4 squares in my mind all the time. The first thing I do is I model it. I draw a picture. That way I keep things straight. I think we've seen enough from myself as well as everybody that mistakes happen, right? Especially when we're doing stuff this easy. I think I was talking with Aaron the other day about how the more challenging stuff we do, the more we forget how to multiply, right? The more you forget how to do just simple, basic things, okay? And that's the way it goes. So this looks like it's 18 inches long by 10 inches wide. And what do I want to do to this thing? What's the problem asking me to do? Find volume. Well, right now it's just area. How is it creating volume? I'm cutting corners. Square corners. X by X corners. And I could just discard those corners, and I'll have 4 sides then that will be folded up, and then they will make a box. Does everybody see how that's happening? When I cut it, I'll fold it up. My goal is then to maximize the volume. So I'm trying to calculate volume. Well, the volume, in terms of, we'll say x being our variable, is equal to length. Well, I won't even use x right now because we don't have that variable stated. Volume is equal to length times width times height, we'll say, right? Well, I need expressions for length, width, and height. Length, width, height, those 3 pieces. So what is my length once I cut those squares off? 18 minus 2x. What is my width? 10 minus 2x. What is my height? X. Now, if I multiply all those together, that will be a formula for my volume, right? In terms of what? In terms of x. So x is my height because I fold it up. So this probably shouldn't say equation. It should probably read function. That's what I wanted it to read. I'll have to change that for future years. So my function would then be x. So volume in terms of x is equal to x times 18 minus 2x times 10 minus 2x. Well, I'll multiply the binomial together first. Volume in terms of x is equal to, let's see, 18 times 10 is 180 and then 18 times 2x and 10 times 2x, 36x and 20x, right? So minus 56x, and then a plus 4x squared. Yeah? Yeah. You betcha. So the volume in terms of x is going to be equal to 4x to the third power minus 56x squared plus 180x. So let's just identify now what the problem's talking about. It's saying that we want to do what? Maximize the volume. Well, if you graph this, what's that thing going to look like? So this just, well, I understand this. This just killed my pre-calculus students when they saw us. Because they said, how high does it go? If we knew how high it went, then we could actually figure it out. And I said, well, you don't know that. You don't know that till calculus. You guys know how to find local maxes, right? It's not, yeah, we do. It's not that bad. We can find that spot. They had to use their graphing calculators in order to do it. Whereas they wish that they could do it by hand. We know how to find that spot. Now, if I take the derivative, set it equal to 0, how many solutions am I going to have? 2, because I have that local max and I have that local min, assuming that this is what the graph looks like, and in fact it does. So now that I have some knowledge about the graph, I can go about actually finding this piece. So as I go back into, I'm sorry, I'm lost here. Let's see, where was I? Nope. Yeah, here I am. Okay, so let's solve it. So we're going to take the derivative, right? So I would say that volume prime of x is equal to 12x squared minus 112x plus 180. What would you do if you saw that? If you factor that, you're much braver than I am. Like Taylor said, let's set it equal to 0. Let's solve it, and let's use the quadratic formula. Okay, let's make life a little bit easier on ourselves. So I'll execute the quadratic formula. I got 12. I've got negative 112. And I got 180. So 7.27 and 2.06. I got 2 solutions. Only one of them's correct. How can you tell? You could look at the graph and try to figure it out that way. You know that the maximum's going to happen first, the minimum's going to happen second. So we know 2.06, but also think about this, you guys. Think about this. What's the biggest x could be? 5. If I cut a box of 5, then I would cut 5 off here and 5 off there. That wouldn't leave me with anything to fold up. So 5 is the biggest that it could possibly be. So in terms of solutions, 7.27 isn't even in my domain. The question is, again, it says find the largest volume. The largest volume happens when x is 2.06. So how would you actually then find the volume? Plug it into what? Plug it into this volume function right here. Not the derivative, but into this volume function right here. So if I go, take my 2.06, y equals 4x to the third minus 56x squared plus 180x, and I go to my table and I type in 2.06, 168.13. What is 168.3? Is that what I said? A for the day. Who can tell me if I plug 2.06 into the derivative, what will I get? I will get 0. 2.6 is where the derivative is equal to 0. Okay? So there I go. Your turn to try one on your own. I will pause this, and you can give it a shot. Okay, if you look back up here, we come up with A prime of W is equal to 320 minus 4W. And so when you solve for it, 0 equals, 0 equals 320 minus 4W. You should get W is equal to 80, and then length ends up being equal to 160 when you plug it back in. Now, with that said, just a word of caution. First of all, as you look at your variables and everything, please make sure that you solve for one variable. Second of all, understand that in the end, what you're modeling is your original picture. So Galen, whether you guys decide to use W on the bottom or on the top, this W represents this piece. So, so you got to make sense with your picture in the end. Okay? So, good job. You took a derivative, you set equals 0, you found a maximum piece. Again, that's optimization at its best. Let's do just one more example. Okay, this is a good example. It says, find the dimensions that give the largest area for a rectangle whose base is on the x-axis and whose corners are at the parabola y equals 12 minus 3x squared. What a great problem. So, doesn't make a whole lot of sense right now, so let's draw it. First of all, I have this box that's inscribed inside a parabola. So what does the parabola look like? Hopefully you know something about this. It goes down. It's symmetrical about the y-axis. It's shifted up how many units? 12. Very good. Good job. So we draw this. There's my x-axis. I go up here. That would be 0, 12. I know that. And it's going to come down just like so. Beautiful. So it says that I have this rectangle that's inscribed inside there. And so I'm just going to draw a rectangle. We'll make it look something about like that. And I understand that, at first glance, you maybe can't think through this on your own. You need to see it. But once you see it, I think you should probably be pretty good to go. So I need to write an expression for area here. And area is equal to my length times my width. So if we would say that the bottom, again it says that the base is on the x-axis. If we would say that the bottom is the width along the x-axis, I need to say something intelligent about the width. Does anybody think they can say something intelligent about the width? Okay, so let's look at this point right here. We will call it x, y. Now, you tell me, does the width have something to do with x, or does it have something to do with y? X. So, if, good job, good job, excellent guess. So, the width is going to be horizontal, which is referring to x. Tell me, if I move my finger over, how many units am I when I get to right here? Half the width, which is x, right? That far over is x, correct? So this spot right here would be x units. So what would this spot be over here? Negative x units. So what's that total distance? 2x. See how I have x units to the right, I have x units to the left. I have 2x is going to be my width. So I have width is equal to 2x. Great. Now, all I need to do is write an expression for my height. Ashley Tavis, tell me, does the height have something to do with x or y? Y. Okay, so it has something to do with y, my height. So let's suppose, people, let's suppose just for a second that x was 2. Let's suppose x was 2. How would you figure out your height? Hint, hint. What? Plug it in. See, your height, your if you look here, you guys, if we plug in x, the function, does it not? The function generates my height. The function generates my height. So instead of y, I could just write my coordinate as x and 12 minus 3x squared. So Ashley says that my height is y. She's exactly correct. But we also know that y is equal to the function value, which is 12 minus 3x squared. So my length or my height, same difference, is 12 minus 3x squared. So that's what I have. I have those. And if I just multiply them together, I get area in terms of what variable? X is equal to 2x times 12 minus 3x squared. Area in terms of x then is equal to 24x minus 6x to the third power. Now, let's just hold on for a second, step back, smell the roses, and say to yourself, wow, that's a hard problem. And we're going to make it really simple. All we have to do is maximize the area. Maximums occur at local maximums, where the derivative is equal to. So see how easy calculus makes things? We take the derivative and we set it equal to 0. What's the derivative of area of x? A prime of x is equal to 24 minus 18x squared. Set it equal to 0. 0 equals 24 minus 18x squared. I know how to solve for that. 18x squared is equal to 24. Divide both sides by 18. X squared is equal to 4 over 3, right? Square root both sides. X is equal to plus or minus the square root of 4/3. Now, I need x to be a positive value, but in this case, it also represents the negative in the other way. The fact is that x is the square root of 4/3. I should probably come up with a decimal for that. And if I do, I get square root of 4 divided by 3, parentheses. I get 1.15. So x, whoop. X is 1.15. Now hold on, you guys. Look at the question. The question originally asks this. Find the dimensions. True or false? 1.15 is my width. False. What's my width? Double that. So the width that we're looking for is equal to 2.3. How would I find the length? What would I do? Plug in 1.15 in for x. 8.03. There are hundreds of more optimization problems. We simply did 4. Good job. I will have a short assignment for you tomorrow that you should be able to get done in class. I will give you the study guide tomorrow as well. What you need to do is you need to make sure that you're working on your curve sketching that we started last week. For tomorrow, I don't know them yet.